Moving on to section 2.3. Section 2.3 is basically a review of a lot of the vocabulary that you learned back in chapter 1. So on page 16 in your notes, it just gives you a little reminder of what a postulate is. So a postulate is a rule that is accepted without proof. And then another reminder of all the postulates that we talked about back in chapter 1. So the ruler postulate was used to measure segments. The protractor postulate was used to measure angles. And then you have the segment addition and the angle addition postulate that we used with that part plus part equals whole. So that's just a reminder because now in section 2.3, we have 7 new postulates. But like I said, this should just be a review of a lot of the vocab from Unit 1. So you have the 2-point postulate, which says through any 2 points there exists exactly one line. And then the line point postulate. A line contains at least 2 points. Then you have the line intersection postulate. So if 2 lines intersect, then their intersection is exactly 1 point. You have the 3-point postulate. Through any 3 non-collinear points, there's going to exist exactly one plane. So in this example, you have D, E, and F, which are your non-collinear points. So there exists exactly one plane, and you can call it plane R. Then you have the plane point postulate. So a plane has to contain at least 3 non-collinear points. You have the plane line postulate. So if 2 points lie in a plane, then the line containing them is going to lie in that plane as well. So if point D and E lie in plane R, then line DE lies in plane R. Then the plane intersection postulate, if 2 planes intersect, then their intersection is a line. So again, this should sound very familiar from Unit 1. So this particular page in your notebook does not require any writing. This is what you're going to use to do the examples on page 17. So what you could do now is just kind of fold that page so that you can still see the title of this section, and then you can go ahead and glue that into your notebook. And again, this is page 16 in your notes. And this will be a really good reference page for you. So you're going to be referring to this frequently just until you become familiar with the wording of all of these new postulates. So if you want, you can kind of keep this open and put it off to the side while you take a look at the examples on page 17 of your notes. So page 17 of your notes are all the examples that you're going to complete using the postulates on page 16 in your notes. So if you take a look, it says in exercises 1 and 2, state the postulate illustrated by the diagram. So now you're just reading a diagram. So reading this particular diagram, we have if, and we have a picture of 2 intersecting lines. Then you have another picture of 2 intersecting lines, but this time with a point that shows where they're intersecting. So you're going to match this up with a postulate on page 16. So if you look at page 16, here it is. Here's the postulate that matches example 1. If 2 lines intersect, then their intersection is exactly 1 point. So that's what you're going to write down for problem 1. That this is postulate 2-3, the line intersection postulate. And then you're just going to list what it states. If 2 lines intersect, then their intersection is exactly 1 point. So that's how you would do these types of problems, just reading a diagram and being able to match it up with a postulate. Okay, example 2, we have if, and we have the picture of a plane. It looks like it's plane S, and it has points M, L, and N inside plane S. Then we have the same picture, but this time there's a line drawn to connect points M and N. So again, you're just trying to match that up with a postulate on page 16 in your notes. And here it is. It's the plane line postulate. So if 2 points lie in a plane, then the line containing them lies in the plane. So that's what you're going to put down for number 2. This is postulate 2.6, and it's the plane line postulate. And again, you're just going to put what it states. So that's example 1, just stating the postulate that's illustrated by the diagram. Inside, you're going to be reading 2 other diagrams. So the diagram that we're using for problems 3 through 6, we have 2 planes, plane P and plane Q, that are intersecting at line K. So you have to kind of imagine that. You have plane P and plane Q intersecting at line K. Points A, B, and C lie in plane P. The only point that is showing in this diagram that lies in plane Q is point C. So point C, because it lies on line K, is in both planes P and Q. So it says, use the diagram to write an example of the postulate. So you're going to write an example of the 2-point postulate using this diagram. So go back to page 16 and read what postulate 2.1 is. It says, through any 2 points, there exists exactly 1 line. So looking at this diagram, I could see that you have points B and C. So through points B and C, there exists exactly 1 line, and you could call that line L. So through points B and C, there exists exactly 1 line, which is line L. Okay, number 4, line point postulate. So go over to page 16 and read what the line point postulate is. It says a line contains at least 2 points. So it's almost like the converse of postulate 2.1. So what you're going to use, again, is line L. And you're going to say line L contains 2 points, points B and C. So line L contains 2 points, and they are points B and C. Then you have the plane point postulate. So the plane point postulate says that a plane contains at least 3 non-collinear points. So you need a plane with 3 non-collinear points. So looking at the diagram, I know that plane P has 3 non-collinear points, points A, B, and C. Alright, so plane P contains 3 non-collinear points, and they are points A, B, and C. And then the last one is the plane intersection postulate, which says that if 2 planes intersect, then their intersection is a line. So we already talked about this at the very beginning before we started anything, that plane P and plane Q intersect, and their intersection is line K. So plane P and plane Q intersect at line K. So that's just using a diagram to write an example of a given postulate. Down at the bottom, you're reading another diagram. So this diagram has 2 planes intersecting. So it's plane A and plane B are intersecting. And remember that they intersect in a line. So plane A and plane B are intersecting at this line here, which is line, you could call it line EF or line ED or DF, but it looks like those 2 planes are intersecting in this line. And then you have points on plane A, points on plane B, and then you have intersecting lines as well. So basically what we're doing here is we're going to read each statement and decide whether or not we can assume that this statement is true based off of all of the different notations that are given to us in this diagram. So can we assume that planes A and B intersect at EF? And the answer is yes. And again, go back to page 16. If 2 planes intersect, then their intersection is a line. So in this case, this is true. Planes A and B are intersecting at line EF. So if you want to put that this is because of the plane intersection postulate, you can. So 2 planes will always intersect in a line, and in this case they're intersecting at line EF. Points C and D are collinear. So again, I'm going to go back to page 16, and it says postulate 2.1, through any 2 points, there is always going to exist exactly one line. So C and D, even though there is not a line that's connecting them in this particular diagram, they are collinear because of postulate 2.1. That 2-point postulate allows us to say that even if there is not a physical line drawn for us in this diagram, that you can indeed draw one and make C and D collinear. So yes, and again, this is because of the 2-point postulate. Line HJ and line ID are perpendicular. So let's locate those. So HJ and ID are perpendicular. And there's your symbol right there. So the answer is yes, and it's because you have a perpendicular symbol in the diagram. So you could put yes, and if you're taking really good notes, you want to put a reason, and that reason is because there is a perpendicular symbol in the diagram. So you always want to make sure that you're understanding why it's yes or why it's no. All right, number 12, GD is a bisector of EF at point D. So remember we talked about these symbols, these little tick mark symbols. You can zoom in if you want. So these two tick mark symbols mean that ED is congruent to DF. So by definition of a bisector, this statement is true. GD is bisecting segment EF at point D because you have these congruent segment symbols. So this is a yes because you have those congruent segment symbols which tell us that ED and DF are indeed equal. How about IH and HG? Is there any symbol in this diagram that tells us IH and HG are congruent? And the answer is no. There's no tick marks there that tell us those are congruent, so this cannot be determined. And then angle HJD and angle HDJ are complementary angles. So I'm going to go ahead and erase my previous markings so I can mark up these two angles. So I have HJD. That's this angle right here. And HDJ. So it's almost like we're looking at this right triangle here. So are you able to conclude that HJD and angle HDJ are complementary? Can you assume that they add up to 90 degrees? And believe it or not, the answer is yes. And it's only because those two angles are part of this right triangle. And the three angles in a triangle have to add up to 180 degrees. And if one of the angles is already 90 degrees because of this perpendicular symbol, so this perpendicular symbol makes that angle 90, that means these other two angles have to also add up to 90 so that they could, all three of them add up to 180. So this is yes. You can make this assumption, and that's because triangle JHD is a right triangle. So the measurements of angle HJD and the measurement of angle HDJ plus that 90-degree angle has to add up to 180 degrees. So the three angles in this triangle have to add up to 180. If one of them's already 90, well, take away 90 from both sides. That means that the measure of angle HJD and the measure of angle HDJ has to equal 90 degrees, which makes them complementary. So this section is really just about understanding all the definitions you learned in Chapter 1 and how they are now reworded into postulates. And now we are using those postulates to read diagrams and make assumptions about those diagrams. So glue this into your notebook. This is page 17. So now we are halfway through Chapter 2.